Hello everyone and welcome back to another video. Today we're going to start with the P1 probability outcome. So probability is quite an intriguing topic because of how often it pops up in everyday life without us even knowing. So some things like a coin toss or making a bet with your friend about which of your favorite sports teams will win their next game all involve some sort of probability. There's also many practical uses of probability, such as warranties, insurance, medication, and weather forecasts. There's many other examples, and I'd love for you guys to try listing 3 of your own here. Now, probability is defined as a prediction of how likely it is that a particular event will happen. Now, we can express probability in a couple of different ways. First, as a fraction, a decimal, a percentage, or in words. We've got our formula here for calculating probability, written as the probability of event A is equal to the number of occurrences of event A divided by the total number of possible outcomes. Now, something to keep in mind is that probability is expressed in the lowest terms, and we'll talk about what that means here in a second. And when you calculate it as a decimal, it can only be between 0 and 1. And again, I'll refer to that very shortly. Now, a specific type of probability is what we call experimental probability, and we calculate that based on measuring occurrences of A in a sample data set, and we try to find out how many times A occurs. Now, to demonstrate experimental probability, let's say I flip a coin 5 times, and I get heads 2 times. So that means that my experimental probability of flipping heads was 2 out of 5. Now, just as a quick review of converting between fractions, decimals, and percentages, we can look at a few examples. To go from a fraction to a decimal, all we need to do is divide your numerator, which is your top number, by your bottom number, your denominator. So 1 divided by 5 gives you a decimal of 0.2. If we want to go ahead and convert that decimal into a percentage, we can just simply multiply that decimal by 100. And in this case, 0.2 times 100 gives you 20%. Now, the last point here, to convert a percentage into a fraction, we want to go ahead and put our percent over 100. So in this case, we have 12%, which is the same thing as 12 over 100. And we need to reduce to lowest terms. Now, reducing to the lowest terms means that we're going to look for the largest number that we can use to divide both the numerator and the denominator. In this case, it's going to be 4. So once we've divided both 12 and 100 by 4, we end up with a reduced fraction of 3 over 25. Now again, just to reiterate my coin flip example, let's say we've flipped it 10 times and we've only gotten tails once. Then our experimental probability was 1 out of 10. Now you're probably thinking, well, what do I call that chance, that 50% chance of flipping heads or flipping tails? And we're going to cover that a little bit later on. Let's take a look at an example. Georgina bought a bag of bulk candies. She counted them and found that 15 were red, 10 were green, and 12 were purple, and 13 were orange. We need to calculate the probability of a randomly chosen candy from the bag being red. We need to express the probability as a fraction, decimal, percentage, and in words. So if we take a look here, we find that 15 of those candies were red. Again, if we think back to our probability formula, we need to figure out how many times the event could occur and divide that by the total number of trials that were had. In this case, the number of trials that were had is really just the number of candies in the bag. If we add up all of the different candies in the bag, we have 15 plus 10 plus 12 plus 13. So that means that we have 50 total candies. So we're looking at the probability of red being out of 50 candies. So probability of red being out of 50. And we know that we started off with 15 total red candies. So that means that our probability is 15 over 50. Now, to reduce that into lowest terms, we need to divide both the top and the bottom by 5, which means that our lowest terms would end up being 3 over 10. So that would give us our probability as a fraction. As a decimal, if I divide 3 over 10, it would give me 0.3. And that would give me my decimal. If I take a look at my probability as a percentage, I'm going to take that 0.3 and multiply that by 100, and I'll get 30%. Last but not least, I'm going to write this in words, and we know that our probability is 3 out of 10. Now, if we're asked, what's the probability of a randomly chosen candy being green or purple? Now, what we need to do here is we need to add the total number of green or purple candies. In this case, we have 10 green candies and 12 purple candies, which gives us 22 candies. So the probability of green or purple is equal to 10 plus 12, which is 22 out of 50 candies. So we can simplify this. If we divide the top and the bottom by 2, this will give us 11 out of 25. In part C, if the distribution of colors in a bag of 1,000 candies is the same, how many would Georgina expect to be red? So we're going to look back at part A, and we're going to look at that percentage of 30. And we can use that to figure out what is 30% of 1,000. All we'd have to do is take that decimal, 0.3, and multiply that by 1,000, and we would get 300 candies. So we would expect 300 of those randomly chosen candies to be red. There's a second alternative solution to this problem as well. We could say to ourselves, if we expect 3 out of 10 candies to be red, it has to be proportional to an X number of candies over 1,000. So now that we've set up a proportion, we can go ahead and cross multiply. So you've got 10 times X, and then we're going to multiply 3 times 1,000. So we'll have 10x is equal to 3,000. We can divide both sides by 10 to isolate for x, and we'll get x is equal to 300. So this is just a second alternative method to helping us figure out how many red candies we would get. Let's try another problem out. After basketball practice, Isabel steps up to the free throw line and attempts 20 shots. Of the 20 attempts, Isabel successfully makes the shot 14 times. First, we need to describe the experimental probability of Isabel successfully making a free throw shot as a fraction in lowest terms. So again, if she has made 14 out of 20, so to reduce this to lowest terms, we need to find the greatest number that we can use to divide both the numerator and the denominator. In this case, it's going to be 2. And we'll end up with 7 over 10. To figure this out as a decimal, we know that 7 over 10 is equal to 0.7. To turn that into a percentage, we're going to take that 0.7, multiply it by 100, and we'll get 70%. And in words, we can say she will likely make 7 out of 10 shots. In part B, it says, for the next practice, the coach wants to make each of the players take 30 shots. How many shots do you expect Isabel to make? We can do one of two solutions. So we can look at method 1. We're going to take 70%, and we're going to multiply that 70% by 30 shots. So in order to do so, we're going to convert that into a decimal, or take the decimal, and multiply that by 30 shots. So 0.7 times 30 gives us 21. So we can expect Isabel to make 21 out of 30 shots. Method number 2 involves us setting up a proportion. So she makes 7 made shots out of 10 total. This has to be proportional to X number of shots made out of 30 total. So we can rewrite this without any of the units. So we've got 7 over 10 has to be equal to x over 30. Once again, we're going to cross multiply 10 times x and 7 times 30. We'll get 10x is equal to 210. We can divide both sides by 10, and we'll get x is equal to 21. So again, we can expect her to make 21 out of 30 shots. In part C, it says, as part of an evaluation, the coach wants each of the players to be able to successfully make 40 out of 50 shots. Will Isabel meet the expectations of the coach? Explain. So if we look at this percentage here, this probability, the coach is expecting 40 out of 50 shots. So 40 out of 50 gives us a decimal of 0.8, otherwise known as 80%. Isabel has a shooting percentage of 70%. So comparing the two, Isabel isn't quite at the 80% her coach is expecting. So no, Isabel only has a shooting percentage of 70%. She is 10% under the coach's expectations. So another thing to discuss when we talk about probability is the sample size. Now, the sample size is the total number of objects or events being counted. Now, let's say we flip a coin 200 times, then our sample size is just 200. Now, the main reason why the sample size is important is because of the types of predictions that we need to make based off of whatever results we get. For example, if we asked 5 people in a math class at Springfield High School if they liked horror movies or not, all 5 of them said yes. It would be erroneous, we would be mistaken if we said that 100% of students at Springfield High like horror movies. If our sample size was maybe closer to 500 students, then that prediction would be a little bit more representative of the population as a whole. Let's take a look at another example. A large cafeteria that serves lunch to more than 400 people per day offers 4 main dishes: spaghetti, a hamburger, chicken chow mein, and a vegetarian dish. Of the first 10 people through the line, no one chose the vegetarian dish. The manager decided to remove vegetarian dishes from the menu in the future. Is this a good decision? And be able to explain your answer. Now, at first glance, we take a look at that sample size. They serve food to more than 400 people per day, and they are looking at the first 10 people. Now, based off of those 10 people, okay, we're just going to forget about the 400 for a second here. None of them, so 0 out of 10 people, chose that vegetarian dish. Because we've only gone through 10 people, that manager decided to pull vegetarian dishes in the future. Now, for those of you with a good business sense, you're obviously thinking, no, that's a horrible decision, and I would agree with you. But let's look at the math. If we look at 10 out of 400 people not choosing vegetarian, then that means we're left with 390 people who have yet to choose their meal. Now, of those 390 people, how many could we reasonably expect to choose a vegetarian dish? We're not exactly sure. So again, without that information, it's really hard for us to make a really good choice, other than to justify the fact that this is not a good business decision. So no, this is not a good decision. Maybe the customers, or maybe vegetarian customers, are further in the lineup. So the moral behind this example is to not be so quick to judge. We'll need to do further research to determine if this is a good or a bad idea. Now, theoretical probability is a little bit different compared to experimental probability but they are quite related. The theoretical probability takes the number of possibilities of our preferred event, and we need to divide that by the number of total possible events. Now, for example, if we're looking at the probability of heads, we have one side with heads over two possible sides, so 1 out of 2 chances. Therefore, the probability of us flipping heads is 1 over 2, or 0.5, or 50%. So theoretically, half of all coin flips are heads. Again, theoretical probability of flipping heads is 50%, but it doesn't mean that if we flip a coin 50 times, we are guaranteed to get heads 25 out of 50 times. Now, if we increase our sample size to something more like 5,000 flips, we'll see our experimental probability get a little bit closer to our theoretical probability of 50%. Now let's take a look at some examples here. What is the theoretical probability of rolling a 3? So if we take a look at a 10-sided die, we only have one chance of getting a 3 out of 10. So that means that our probability is 1 out of 10. If we look at an even number, there are 5 even numbers on a 10-sided die. So that means we're looking at 5 out of 10, or when we simplify it, it'll be 1 over 2. Next, rolling a number equal to or greater than 7, that means we're looking at 4 possibilities, 7, 8, 9, or 10. So that means we're looking at 4 out of 10, or 2 over 5. So if we take a look at this first question here, probabilities lie between 0% and 100%, or between 0 and 1 when written as decimals. Something to keep in mind is when we look at events where a probability is 0, it means that it's impossible. Or when we're looking at an event where the probability is 1, that means that it is what we call a certain event. If we try to describe at least 2 events where the probability is 100, then we could simply say the probability of flipping heads or tails is equal to 1, because we can't flip anything other than heads or tails. We could also look at the probability of choosing a card that is red or black out of a standard card or a standard deck of 52 cards, and that will also be a certain event, or 100%. Now we want to look at the idea of odds. Odds and probability come hand in hand, but are a little bit different. The odds of something happening is what we call a ratio, representing the number of desired events compared to the number of undesired events. So our odds can be shown as the number of desired events, so the things that we want, compared to the things that we don't want. So for example, the odds of getting heads on a coin toss is 1 to 1. There is one head versus your other possibility, which is tails, so 1 to 1. Now your probability, on the other hand, is 1 out of 2, or 50%. We need to make sure that we simplify our odds whenever possible. So for example, we can turn 5 to 10, or your odds of 5 to 10, to odds of 1 to 2. In the first example here, if we roll a standard 6-sided die, what are the odds in favor of rolling a 6? If we think about how many 6s are on a 6-sided die, there is only 1. We are going to compare that to the 5 situations where we don't roll a 6. Now, if we're thinking of the odds of against rolling a 6, now we want to think, how many possibilities are there where we don't roll a 6? Well, we could roll a 1, 2, 3, 4, or a 5. So there's 5 possibilities against rolling a 6. Compare that to the 1 possibility of rolling a 6. We can take a look at the second example. If you draw a random card out of a deck of 52 cards, what are the odds in favor of drawing a black card? So in a standard deck of 52 cards, half of them are red, half of them are black. So that would mean that 26 to 26 would be our odds. Or we could simplify this down to 1 to 1. Against drawing a face card, so each suit, so we have 4 suits, each one of those suits comes with 4 face cards. So that would mean that we have 4 times 3, so we have 12 face cards that we don't want. And we have the other 40 cards that are not face cards. So if you look at part C, in favor of drawing a 6, remember there's a 6 of diamonds, there's a 6 of hearts, there's a 6 of spades, and this is my best impression of a spade, and the 6 of clubs. Again, remember I'm a math teacher, not an art teacher, unfortunately. I'm sorry. And we have your spade and your club right there. So we have 4 possibilities in favor of drawing the 6, and we're going to compare that to the 48 possibilities where you don't draw 6. Now we can simplify that 4 to 48 by dividing both sides by 4, and this would give me 1 to 12. Now against drawing a diamond card, we can think about it first in terms of drawing a diamond card, and that's our undesired event. There are 13 possible diamond cards compared to 39 that we do want. So 39 desired events compared to the 13 undesired events. So again, we can reduce this to 13 to 1 by dividing both sides by 13. We can also look at odds in terms of word problems. Alexa has a small gardening business in Victoria, BC. She planted 14 daffodil bulbs. She planted 14 daffodil bulbs in a client's garden in the fall. In the spring, 12 bulbs flowered. So based on these statistics, what are the odds in favor of a bulb Alexa planted in another garden flowering? So we're going to take a look at exactly what happened. We're looking at odds. So again, odds means that we're going to look at some sort of ratio of our desired events compared to our undesired events. So looking at our desired events, we're going to take a look first at the fact that 12 of those bulbs flowered. So we had 12 out of 14 flowering. So 12 is our number of desired events. Now, how do we figure out the number of undesired events? Well, all we need to do is we're going to take the 14 total events, subtract the 12 desired ones, and we end up with 2 undesired events. So once again, we're going to simplify this by dividing both sides by 2, and we get 6 to 1. Those are our odds in favor of another bulb flowering. Now, what's the experimental probability that it will flower? Well, we're going to take a look back at what I wrote down earlier, 12 over 14. So that was our experimental probability. And again, we can reduce this by dividing both the top and the bottom by 2, and this will give me 6 out of 7. We can take a look at another example here at number 7. So there are 12 green, 4 blue, 15 yellow, and 7 white marbles in a container. What are the odds in favor of a randomly chosen marble being white? So we're going to look at the number of chosen marbles, or number of possible marbles being white. So there's 7 total marbles that are white. And all together, if we were to count up all of these marbles, 12 plus 4 plus 15 plus 7, that will give us 38 total marbles. So if we're looking at the odds in favor of it being white, there are 7 desired events. Now we want to compare them to the undesired events. All we need to do is take the 38 marbles and subtract 7 to give us 31 undesired events. So our odds are going to be 7 to 31, and we can't reduce that any further. If we're taking a look now at our odds in favor of something being a color other than yellow, now if we take a look, we have 15 yellow. So if we take 38 minus 15, this would mean that 23 marbles are not going to be yellow. So this would mean we would have 23 possibilities of something other than yellow compared to our 15 that are yellow. Now we're looking at the probability that something is going to be, or that our marble chosen is something other than yellow. So again, we had 23 of the ones that we want divided by the total number of events, which in this case is going to be 38. So we can see how we compare and contrast them. Again, if we want to add both of them up, the total number of desired versus undesired, these numbers should add up to give us the total number of events when calculating your probability. So that's the end of today's video. I hope you guys found some interesting facts about probability and maybe some tips or tricks that can help you win the next coin toss against your buddy. Thank you so much for watching, and I'll see you guys in the next video.